Hello. Good morning.
Hello, Asko. Good morning.
Morning. Can you make me a presenter so I can share my screen?
Yes, let's try immediately. I will make you a co-organizer, so for sure you should be able to share your screen if you want to try.
Yeah. So, okay. So you should be able to see my slides.
Not yet. Does it tell you that you're sharing already?
Let me check. Okay, I had to click this one small button also.
Okay.
Yeah, and
Yeah, I can see
it should work now.
the background. I think not your slides.
Now
Now
it
your
should.
slide. Yeah.
Yeah. Okay.
Okay. Good.
So let's wait a bit then.
Yeah. At least 5 minutes, I would say. The schedule starting time.
Yeah.
Then we'll see also with Issam and Anis how many people we are expecting. Maybe we can wait a couple of minutes more, I would say.
Yeah.
Okay, so I guess we've waited long enough. So thank you everyone for coming. Thank you, Asko, for giving us this this presentation, the opportunity to have this training. The event is recorded, so just for everyone to know, and the recording will be uploaded on the shared folder together with all the presentation that we're going to see today, and maybe also some additional material if necessary.
Yeah.
I don't know if Issam or Anis wants to say a few words. Otherwise, I would give the floor to Asko to start.
Thank you, Daniele, and good morning, everyone. Maybe Issam, you can just quickly, very quick introduction. You are muted, Issam, I think.
Yes. So I was talking. Thank you, everyone. I was talking. Thank you for your participation and involvement in this first training capacity building, which will be the succession of other training building, capacity building trainings, which will start from today until the end of the project, if Iliad project, and I would like to thank you all, thank ASCO for providing the training, and thank the participants that will participate. And if you have any question, so you have, I think, the agenda shared and the last email that that has been sent to you. We will send it also in the conversation if you would like to check it and see it. And if you have, as Daniele said, and Anis, if you have any question, so just put it in the discussion, and then after the presentation, we will help, like Asko will answer your questions, and so yeah, I think enough for me. I leave the floor to Asko to continue the presentation.
Okay. Thank you for the introduction. So I will just share my screen and the slides in a sec. So, hi everybody. I am Asko Ristolainen. I'm from Tallinn University of Technology, from the Center for Biorobotics. And in today's short training session or in this presentation, I will talk about the sensor that we are providing to Iliad partners and we are using ourselves. And I will talk what the HydroMast is, how it can be used, and where it can be used. Just a short agenda. So I will give a background overview of the device that you can see here on this picture, how it works, where it can be applied, how it can be installed, and what future developments we have planned with this device. So just the background information. The device is called HydroMast and was developed previously within another Horizon 2020 Project LakHsMi that ended now already 4 years ago. But since then we have applied them in many different applications. So the device itself is a small, quite cheap point measurement device that allows to take measurements near the seabed, or actually that was what it was planned for initially. It's bio-inspired, and just a short information about the bio-inspired aspect. So fishes have these small superficial neuromasts on their lateral line sensing mechanism. And we took this idea and made it into a sensor that you can see in the picture in here. So this is the very first prototype back in 2016, where we used accelerometers and 3D printed parts. And since then, we have developed this sensor further to be usable also in field applications. So now about the sensor itself. The sensor uses a vibrating mast, and by looking at this mast vibrations that is fixed to this base through a flexible membrane, we're able to measure flows, flow directions, and we are using two different measurement techniques. In order to measure the tilt of this mast, what we are using is a 3D Hall sensor inside the body of this device, and we are using two ways to measure flows. First of all, we use the tilt of this mast to say how strong the flow is. So this means that we can measure the velocities instantaneously. And the second method that we're using for measurements is the vibrations that are caused by the flow. So if the device is in a flow field and the flows are continuous, there are vortices that are shed off from this mast. And by doing a Fourier transfer on these vibrations, we can then correlate it back to the continuous velocity. So the second method is basically used for averaged velocity estimates. And also we can tell the flow direction from the mast tilt, so you can also say where the flow is coming from. And also inside the body of the device, we have an incorporated absolute pressure sensor. So we can measure the waves at the shallow waters, and also sea level if the device is installed at higher depths. So more about the overview of the sensor. The sensor can measure flows in different flow ranges, and it's dependent on the height of this mast. Also, we can have different kind of pressure sensors on the device to allow the sensor to be installed deeper, or if we want to have higher resolution of the sea surface fluctuations, we can have a smaller range pressure sensor on board. Some information about the resolution. Accuracy of the device is it's calibrated and compared against a Nortec Vectrino ADV in a lot of validation experiments. And from the device, the data output can be selectable, although the device itself is working at 50 Hertz, so you could get instantaneous velocities out from the device at quite high rate. And the communication of the device is working at with the RS485 protocol, so we can have really long cables on the device. And some samples of some long data sets and some short instantaneous velocities. So currently in Iliad, the main aspects that we are working on actually is building communication possibilities for the device. So there are various ways you can get the data when it's installed somewhere in the sea or in the river. Directly from the device, as I said, you can use USB or RS485. That allows a communication up to, let's say, 500 meters from the device itself. Then what we have built to connect up more sensors are these sensor hubs. With that, we can we use a mini computer inside there to interrogate the device, but also pre-process the data. So we use currently BeagleBones, but previously also we have been using Raspberries. And with this sensor hub that can then be connected via Ethernet, via GSM to the network. You can use Wi-Fi. And currently the latest development is that we are starting to use also radio signals to send the measurements to the users. And also serial connection is also possible with the sensor hub. So there is also a possibility to use the sensors offline. For that, we have a battery pack that can be installed underneath the sensor. So, how to access the data? The data is then, as I said, pre-processed in the sensor hub, and the data is then sent via MQTT protocol to Amazon cloud server, where the data is stored. And then the data can be accessed through AVS API for the different pilots. And here on the video, you can see a sample scenario where the devices were installed in our own lab. Basically, we generated artificial flows, let's say. The sensors were picking them up. And then, okay, it doesn't play. Then at the end, we basically have a graphical user interface where different installation sites can be chosen, and data outputs can be viewed in this web interface. So yeah, just a picture of that. This is also being updated at the moment, so for our own testing purposes. So the energy consumption of the device is rather low. The sensor itself uses just below 150 milliwatts. It can be powered, the minimum is 5 volts and it can go up to 12 volts. The input voltage. Then with Ethernet possibilities, it's just below 3 watts. When we are using GSM, this is actually the most costly possibility. It would be around 6.5 watts. With Wi-Fi, it's also quite low, and with LoRa, it's also quite low energy-wise. So, but now I will talk about shortly about the installation possibilities. So the HydroMast should be installed on rigid surfaces or structures to avoid movement of the device base during measurements. The HydroMast has mounting holes at the bottom of the device. So there are 4 M6 holes onto what we can install different brackets or mount the device directly to a structure. Then also it should be installed away from obstructions to avoid disturbances of vortices from nearby objects. Then we also have learned that cables of the sensor should be fixed on structures to avoid wear and tear. On the device, we are using wet connectors, so that allows stepwise installation, for example, in harbors, where the installation frames can be mounted on rigid structures. After that, the cables can be fixed and the sensors can be actually connected underwater as a last thing. And here is an example of field work happening in one of the ports in Estonia, where we installed 16 of such sensors. Now I will show you some installation options that we have used previously in our let's say pilots and test sites. So we have previously, as I said, worked in harbors where we installed our sensors to pier posts under the pier with a rigid frame. We have also installed our devices on pier walls with some metal profiles. Also quite easy and fast way to produce. Then on the seabed, we have used concrete bases for installation with offline devices. So this just make sure that our devices are upright and fixed quite well. Then also we have used metal frames for installation on the seabed with offline devices. And yeah, also some metal frame examples in more harsher conditions. Now, we have also done installations with large frames on the seabed. Here on the left bottom image, this frame was 5 by 5 meters, but here on the right hand side, this is an installation of 9 of these devices for measurement of seabed stress and velocities in Bay of Riga last summer. And this frame was 20 by 20 meters. And now I will talk about applications for our sensors that we have done already. So first of all, we have worked in rivers quite a bit. So first of all, that allows us to do very nicely sensor validations. But we have done studies where we investigate different flow types, turbulent and non-turbulent flows, then also fish habitat investigations, and also monitoring flow changes over longer periods. So you can find actually papers about these works in these articles below. Then secondly, we have been working on the coastline for measurement of ship wakes and monitoring also ship traffic. So a very good example is in Tallinn Bay. In the summer period, we actually have a lot of large ships and cruise ships coming into the port. And this, first of all, affects the sediment motion in the seabed if they're not following the speed regulations entering the port. But when we are measuring in an array of these sensors, then we can also monitor where those ships were traveling, because the ships generate wakes when they pass the beach. And when we have the velocities and also the wave fluctuation, then we can tell what ship was actually passing by our sensor grid and how fast and where it was going. But yeah, on the coastline, then also doing sediment motion studies and giving validation data to seabed modelers and sediment transportation studies. Then in harbors, monitoring currents for harbor traffic safety. And then also you can have distributed sensing at different depths in the harbors to understand at what depths the water is moving and give this information to harbor captains to allow them to dock big tanker ships. And in this application with our sensors, we were giving the live velocity information to the ship captain, so they were able to understand how should they approach the docks and what currents to expect and to avoid challenging or dangerous situations. And on the seabed, we have done some studies for measuring currents for renewable energies. One of these examples was done in the Orkney Islands in Scotland, and in the Baltics we have used our sensors at quite high depths, up to 70 meters, if I'm correct, to do measurements of a natural water movement caused by thermocline. This is a natural effect that is happening here during summer period when hot and cold water levels are mixing and causing and creating currents like that. So also last summer we installed our devices in Svalbard, Norway. That is very far in the north. And the point of this study was similarly to understand how are the currents moving over the winter period. So these devices were installed in last year's September, and they're still there measuring. So we're hoping to get those devices back somewhere in this summer when the sea ice has melted enough. Then also we have applied our devices in fish farms. We tested our previous versions of these sensors in a fish farm in Norway, and we're able to measure flows through the fish cage, and that basically indicates if the fish nets are clean enough, if there is enough water motion to allow the fish to be healthy, and the currents through the fish cages are also important for transporting the waste from the fish cages. And finally, sediment transportation studies. We did a big study in August last summer, where we, as I said, installed a 20 by 20 grid to give validation information for sediment transportation modeling. And this was done part of an Iliad project. So in Iliad we have a pilot where we study or try to give or we try to improve the sediment transportation modeling by giving researchers validation data for their models. And there can be a series of alternative applications for our devices. As I said, if we would put our sensors up online, we can do online shipwreck detection and possibly monitoring what is happening on the coastline. Sensing flows in extreme conditions as seen in here. Perhaps when we can put our sensors to ship hulls, monitoring biofouling, and so on. So there are a lot of different applications we have tried and will probably try in the future also in Iliad now. And the future plans for our devices are basically the improvement and development of telemetry solutions. Now we're integrating our sensors into the pilots and giving the pilots live data streams for currents and waves. And also we are working currently in embedded software implementation, meaning that we want our devices to give out the velocity and wave information directly. So this is an ongoing work, and currently we're running also longevity tests by our own pilots, but also probably going to do that in Mediterranean, as we haven't been in there with our sensors yet. So to conclude, thank you for listening. If you have any questions, I'm happy to answer, and you can find our contacts in here. So thank you for your time. I know that most of the pilots already know our sensors, but it's a good way to repeat this information, I think, and hopefully others who are listening to this with this recorded session, then also can contact me directly if you have any questions. So thank you.
Thank you, Asko, for this introduction and for the presentation. So we have two questions from Slim. The first one, it is FN the natural frequency of the HydroMast sensor?
Yeah.
How FN is determined?
Yeah, so the FN is the natural frequency of the HydroMast. So we basically we place the sensor inside the water. We tilt the sensor and let it get back to its original state, and we measure those frequencies that the sensor have both in water and in the air.
So I don't know if
Slim still here.
If Slim have to react or it's okay as an answer. Otherwise, we go to the next question of Slim also. He has another question. In shallow water, how can we Right.
So how can we distinguish between orbital velocities due to the water and currents induced by other driving forces? So yeah, we basically would need to have a background measurement somewhere outside the point where we're measuring to remove the background motions. And unfortunately, with the current device solution, we can't. We have to have the device fixed, so we can't really do measurements when this device is moving. So in this shown study, we had a device that was equipped with two IMUs. So one of them was measuring the tilt of this mast, and the second one was measuring the motion of this sensor body. So that way we're able to somehow extrapolate the velocities, although this was not easy. But with the current device, we're not using IMUs on this vibrating mast anymore. And there are one main reason basically for that is because actually two. One of them is that this IMU cabling coming through the case is a first point of failure. And secondly, IMUs are more expensive to use on measurement devices. This Slim has a question how it was anchored. So we basically had an array of sensors. So we had a buoy on top of the water, and then let's say a heavy anchor just floating inside the fish cage. It was about 15 kilos, if I'm correct. Yeah, Sam has a question.
Thank you for your presentation. I have a question. In your opinion, this kind of data can be used for some comparison with the optical satellite data for like a sediment transportation by using the optical data from ESA? I think it's possible. Because we have the same methodology with the wind energy or wave energy to find the RMSE or some accuracy measurement for forecasting regarding the in situ measurement like buoy and the satellite data. I want to ask your opinion. This kind of method. Yeah.
If you are then. Yeah, in situ we can measure the currents and the velocities at the desired depth. But in order to compare a sediment motion, then you have to have a model to compare against that also. So what we are actually now planning to do is to work also with the Port of Valencia, and over there. DocTech is just started already the pilot to monitor the sediment buildup from the sonars of the pilot ships, and the idea is that we would place our own sensors also near the sites where they're doing the measurements to understand how the currents are affecting the buildup of sediments. That is one way, and secondly, currently we are working of getting our own sediment model working. So we have partners here in DocTech that we are working with, but also we are working with Georgios from VP2 to get to try and use their sediment model. So let's see whose model we get to implement first. So yeah, I think. There is a way to try to do a comparison between satellite-based and model solutions.
Thank you, Asko. Also, I have another question. In your study, you usually use the individual measurement data, or you will use it like a package, or in better sense, like a region of interest of the data?
Sorry, can you repeat?
because when you installed a lot of in situ measurements, so you have a kind of package on the port area or harbor area. So you will use the each of these installation as an individual data for measurement, or you will use the all measurement data as a package of the area.
So in this study, we have actually the both solutions. Of course, we can have the look at the individual measurements, but also we can combine the measurements. And this is actually that we are trying to do in previously in the harbor case when the harbors where the harbor was having a pier that was built on both. So we installed the sensors all around the pier because always from one of the directions we would have the shadowing effect of the pier. So in that way, we're doing also filtering of the measurements to try to understand which of the measurements were disturbed and which were not. So it really depends on the applications. If they're all in clear water flows without obstructions, then you can put less sensors or try to have a median of these measurements.
Okay, thank you.
Okay, I see Sim had another question regarding the autonomy and the sampling rates. So the sampling rates for the pilots is really dependent on their needs. Currently, we are testing at 15 minutes on our test site, but it can be higher. And yeah, the batteries, if we have a remote installation, then we want to basically measure less frequently to have longer battery life, but currently we are using just regular alkaline batteries on our offline devices. But this is really up to the installation or where they will be used, so modifiable.
I think also there is a question from Steam about the batteries too.
Yeah, I just answered the batteries that we are using are for the offline devices, just alkaline batteries, but different kinds can be used depending on the requirements. We probably put up, we have an installation in Italy coming up where we probably use something different from alkaline there. So rechargeable solar power batteries, LiPos most likely.
Thank you, Asko. Maybe I have also a question regarding the use within harbors and in general, even in rivers, because do you face some issue regarding some macro litter and plastic bags in particular? If it is, I mean, stuck there, or because you know, in the harbor, when the engines start working, sometimes it makes everything moving in the water, and it could happen.
So if we are working in salt water, then these devices, the working part, this mast is covered with copper. So what happens with copper in salt water that it creates oxidation layer on top, and actually this way we avoid biofouling on this mast because nothing wants to grow on this oxide layer. But yeah, the problem we still face with these physical devices is if we have some debris or some vegetation that gets stuck on the device, that has to be cleaned. So yeah, maintenance-wise, the device should be checked like every 3 months perhaps. And of course, then from the data that we receive, we'll see if it's grown full of something. But this problems remains, I think, with most devices. If you have some debris stuck on the device, you can't like really avoid that. So yeah.
I think it's quite useful. I mean, and my other question, and how to know how many sensors we need. I mean, according to our needs. Do we need 3? Do we need 10? I mean, how this is made?
So it really depends on the application. Of course, first of all, we have approached the pilots. Let's say we do like a test case. We send you like a array of 2-3 sensors, so we can see if the solutions, the communication, everything is working. We have a test period to see if the sensors are wearing out, if the cables are holding, and so on. And then, yeah, if we see that the solution works, then we can widen the, say, area of interest for the pilots.
Thank you. And from the pilots, if there is still additional questions.
I have a question from my side. How do we know that the sensor is not working or is given wrong information? You know, because I don't know, the materials made of this sensor, which is copper, maybe will be oxided with salt water. So maybe, we don't know, maybe there will be some misinformation or somehow there are information are wrong. So I don't know.
Yeah, good question. Actually, what I showed in the very beginning, we are using 2 different ways of measuring velocity. One of them is just the tilt angle, and the other one was the vibration mode, when we are looking at the vibrations of the device. And one of the clear indicators that something is wrong is that if something gets stuck on the device, you won't get these vibrations anymore. And these 2 measurement methods don't, they're not matching up anymore. So that is the first indicator. But there are some other matrices that we have looked at, like the noise level from the frequency ranges of the device and so on. So there's different ways to detect those disturbances, and of course then the system will notify if something is wrong and should go and check on the devices.
All right, so and in this case, it will be easily extracted out of the water, then refix it if something happens. So
yeah, so this mast is just a screw-on mast. This membrane in here is very easily replaceable if it gets damaged. So and these parts you can all remove and change without opening up the device actually. So you don't have to go into the electronics, and this can be done in the field actually without opening up the device.
great.
By in the field, you mean underwater? Or you
Yes.
have to, okay.
I think, yeah, this can be done also underwater.
Okay, but maybe the other, this is also another question. If there is any possibility to use it for fisheries, I know that this is a big constraint. Unfortunately, the tool is quite useful, but if you put it in a fishing area, there is the risk, unfortunately, to be, I mean, even trapped within some nets. Because I'm just thinking about marine protected areas and no-take zones, because I saw that this tool is also, the sensor, sorry, is able to give you if there is any activity of shipping activity there, which could be also useful for these managers in these kind of areas.
Yeah, if we want to monitor the ship like motion and action, then you really need to be in more shallow waters. So you can see like kilometers of what is happening on the seabed just by looking at the water fluctuations, because from wakes of the ship you will get like a different set of impulse of waves over time, and then you can, if you have an array, you can check like where was this source coming from.
Okay, thank you.
So it's not detecting the ship while it's not moving, only if it is going. So the sensor.
So in order to detect ships, for the waves you use the internal pressure sensor basically. So you look at the changes in the waves, so you will get some irregular waves basically when the ship waves are passing by. But of course, yeah, you can also use the velocities to see if there is a spike in the velocities, because usually ship wakes are stronger on a regular day. But if it's on a stormy sea, that processing is a bit more difficult probably.
Yes.
So if I understood well, it can be used both for live data, let's say to live monitoring, but also to have this kind of modeling. I mean, to help improving some modeling and get field data, which I found quite useful. I mean, both uses are quite useful.
Right. Yeah. This is exactly what we are trying to use our sensors for in our own pilot. We have partners developing sediment transportation models, but they are also quite often just depending on the measurements of radars, of satellites, to see what is the surface doing. And they have models of the waves, like what is the velocities induced by these waves on the seabed, and from there they calculate the velocities transporting those sediments. But what is actually happening due to the conditions, the bathymetry of the seabed, they don't really actually measure that, and this is very expensive and tricky to do in these shallow water areas. And well, last summer we were able to do. I think this is one of the first data sets with sensor array measuring, let's say, benthic flows from waves in the Baltic Sea. So this data set is, I think, quite valuable. And even better if you can put it up online, which is not so easy if you are working with storms.
What are other questions for the pilots? If you want to ask any other questions, so feel free.
Yeah.
To ask or
then
to send chats.
Just if you are interested in using our sensors, then please feel free to contact me. We have already, I think, talked to most of you, so you know our sensors, and we are already in progress of getting the sensors to you. So, but if there are some open questions or someone missed out the opportunity, then let me know.
We have Andrea who raises her hand, so please feel free to talk.
Yeah.
Sorry. Sorry.
Yeah.
Can you repeat? I don't hear.
Andrea, I saw you
properly.
raising your hand. Sorry, I don't know if it was by accident or you just wanted to ask a question. I saw your hand up, so.
No. Was a mistake. Sorry.
Oh, okay. It's okay.
Right, but if we don't have any other questions from my side and from your side, then I hope from hear more from other pilots, and hopefully can get our sensors to the pilots we are talking already to soon.
Yes, sure. And even if later on, I mean, for the pilot, you still have some additional needs, additional question, just come back to us and highlight this. And I just want to use the opportunity to ask you, to thank you very much, because you gave us a very good presentation, and I think this tool, this sensor, will be quite useful for several pilots. And I saw that you already planned their use for some, and you already start with others. So maybe a feedback later on from the pilots themselves would be quite useful. And also, if they have some advices to improve something, or even to give some advices to the other pilots whenever they will address future needs, would be great.
We are very, very interested of getting feedback, because this helps us also with our developments, and we will be in close contact with the pilots even after our devices are installed. So
another thing, Asko, well, thank you for your time and also for the well explained presentation. Just if you would like to share with us the presentation, then later on.
Yeah, I can send you a PDF copy of that.
All right, it would be great.
Okay.
So, Daniel, if you could, like in the end, like save the recording, it will be very useful, along with the presentation in PDF, and then we will circulate it to pilots and for everyone who is interested to know more about the sensors. And if he like tries the sensor, he send us his feedbacks, or he feel free to contact Asko. So yes, in this case.
Yeah, absolutely. You said it all. So you'll find, as said before, the recording in the shared folder and the presentation, and of course we'll send another email with the link to make it easier for you to find it. Thank you all. Have a good day.
Good.
Thank you.
Thank you.
Bye-bye.
Thank you, everyone. Thank you for your participation.